Okay, guys, we're back to action. We're going to get back to where we were in the document. Let's see if we can find it. May have lost it. What were we on? So, if we look at this document on the web page, we said that I think we were at, we see light when electrons have been promoted from the ground state to the excited state, return to lower energy states, finally to the ground state. So essentially what we're saying on that is, if we show the ground state as being like level 1 or something like that for an electron. Now, do all electrons have to be in the ground state as number 1? No. If you've got 5 electrons, you have to have 2 electrons in the first level and 3 electrons in the second level. And actually, you've got 2 in the S, and then you've got 1 in the 2p. So they would be like this. So what we're saying is, if they get excited, they gain a photon, and this one maybe moves to this level, just like it did in all the videos and all the simulations. When it gets up to here, it doesn't like being there, does it? So as it falls back down from that level to this level, it would give off a certain photon. So whatever the energy was it took to get from here to here is the same energy it takes to drop back down to that point. If we're lucky, we might be able to see that. What would be true if this electron dropped from here down to here compared to these two? Let me ask you that again, because now I think most of you are back on track. How would this photon compare to this one? We'll call this number 1. We'll call this number 2. How would the energy of photon 1 compare to the energy of photon 2? Number 1 would have, energy-wise, would be greater than 2. How about frequency? Which one would be a higher frequency wave, number 1 or number 2? Number 1. Which one would be the biggest or the longest wavelength? Number 2, because that's going to come up here in a minute. Energy and frequency are directly related, but energy and wavelength are inversely proportional. Everybody okay with that? All right. So that's all we're saying is really there. Just make sure you understand all those labs we did all basically boiled down to this statement. What do? You promote electrons. They fall back down to give off energy. That's how they were able to determine that there must be energy levels in atoms. So why do electrons behave the way they do? Because they aren't really things, are they? They're waves, and waves behave differently than particles do. So basically, waves behave differently than particles. The rules for waves are different than the rules for particles. How about that? Look at the periodic table and tell me what orbital outer shell electron is for an element without writing its electron configuration. So if I have an electron, and let me go get a periodic table. If I ask you, for example, if I ask you where this thing would be in terms of what does the electron configuration of, let's try it again. What does the electron configuration of tellurium end in? Now, I cannot force you. I cannot. There's no way in the world when you're sitting there taking your test, I can get into your brain and say, oh, I don't want you to look at that period. I don't want you to write out the electron configuration to figure out what this ends in. I mean, you can do that. You can, quote, cheat on me if you want to. My point is, can you do it by just looking? What does that electron configuration end in? 5p4. Because here's 5. This is p1, 2, 3, 4, 5, 6. Don't count helium. So this ends in 5p4. 5p4. Now remember, these rows are behind. This is 3d, 4d, 5d, 6d. This is 4f, 5f. So this is 5s2, 4d10, 5p4. So this would be krypton, 5s2, I don't know what happened there, 4d10, 5p1, 2, 3, 4. That saves you a lot of time. What's the dot diagram for tellurium? Remember what I told you? If you look up here and look at the group number, the Roman numeral, or some of them, the A number tells you the valence electron. So this is 6A. So look, here's the S electrons and 4p electrons. So tellurium's dot diagram is 6 dots. Ends in 5s2, 4d4. Now technically it ends in 5p4. Okay? All right, now what if I think the next statement, all right, we'll just leave that there if we need it. I think the next statement says, if I'm not mistaken, let's see. It says, we said be able to look at the periodic table, tell what it's in. It says, given an electron configuration, determine what element's being described. So what if I said 1s2, 2s2, 2p6, 3s2, 3p3? Now there's three ways to get this answer. All you have to do is add up all the top numbers. That's the easiest way to get the answer. What's all the top numbers added up? 15. What is element 15? Phosphorus, right? So that's phosphorus, element 15. That's the fastest way to get it. But what could you do? If you understand, you go 3p3. So what do? You go get, where did I do with that? I wonder where that is. Where'd that periodic table go, I wonder? Let's just call it back up over here. Huh, lost it. There it is. 3p123. There it is. So 3p3, it's phosphorus. There's the second way you can get it. Third way, what? Just count. Just go, 1, 2, 1s2, 2s2, 2p6, 3s2, 3p3. Just count over till you get to it. That's a pretty easy way to do it too, isn't it? All right, now, where are we? That's not right. Let's go back. Describe and determine the number of valence of electrons in an atom. Use the number to write the Lewis dot diagram. We already went through that, didn't we? Everybody okay with that? Bohr model picture, just draw a picture of an atom and put the proper number of electrons, just like last test. I think almost everybody got that right on the last test. I'll just have you do that again. Hey, what if I did this? Well, here's a nice question that I'd love to ask every year. They'll give you a little artificial, periodic table that they've drawn. Right? What does that electron configuration end in? Two S2? Or could I do this? Could I go 1s2, 2s2, 2p6, and maybe this one's marked like this, and it'll say, which element has this electron configuration? So, you know what I'm saying? You may see a periodic table with A, B, X all over it, something like this, And I'll ask a question, and you'll have to pick one of the letters. It's kind of like matching. It's matching, but there'll be a question that'll be associated with it. Which element would end in that configuration? Oh, that's C. Okay? That's not too bad, is it? All right, now we're going to get rid of some stuff on the paper. Maybe. That looks like that was a review for the test this morning. You know what? I probably just need a new copy of this. Where are we? Honors. We're running out of time here. Honors, electrons, worksheet. Does anybody see? Oh, what just happened? I just want the review guide. Where is it? Well, let's do it the easy way. Let's just go to there. Review sheet. Where are you? There it is. So what are we down to? We are down to... That was the one I was talking about. Put various elements in their proper position based on the configuration. Valence electrons we did. Bohr model we did. This question very simply would be, what element would oxygen act like? Which element would oxygen act like of this group? Okay? Would it act like? So for this question right here, by the way, we're going to mark out this whole thing. We're going to mark out this part. We're going to mark out this part. So if I have oxygen, will it behave more like Mg, Cu, Rn, or S? Why? It's in the same family. So an element in the same family, by the way, it should be a little n. If you're in the same family, then you will behave like the others in your family. Easy enough on that? Okay. All right, you ready for the additions? No, maybe not. So let's go over and get the additions. We may run out of time here. Looks like I'm probably just going to have to add them. Oh, no, here they are. Okay. So here's the additions. Sorry about my chicken scratches. Know the parts of a wave and be able to label them. Everybody okay with that? What number are we going to call that? We don't have numbers, do we? So here's one. Looks like we're going to have to go to a third video. Calculate wavelength, frequency, or energy given at least one of those variables. Make sure you can convert nanometers and centimeters to meters. That's centimeter and nanometer. For centimeters, divide the number of centimeters by 100. For nanometers, divide by 1 billion. Make sure you know that the electromagnetic spectrum in energy terms, and you should be familiar with those 7 portions of the spectrum in order. Okay, so if I ask you on the test which has more energy, a gamma ray or a radio wave, you should know. So there's 7 portions of the spectrum. Anybody going to come up with a sentence for that? I can't even think of a good sentence for that to go with it. RMIVUXG. Anybody got one? We only have 20 seconds for you to come up with it to help them out on the video. All right, I got to cut this off. It's going to cut it off for me. We'll see you on the next video, part 3.